Today you will find out how to create advanced facade pattern contained from several hexagonal modular elements that are positioned in a certain order based on facade openings. This tutorial is inspired by the project Lane 189 located in Shanghai, designed by UNStudio. If you follow all the steps, you may significantly improve your skills regarding data tree and complex surface splitting. Let's get to it. Hi guys, Salazar here. Before we start, if this is your first time here and you want to learn how to use Rhino and Grasshopper, start now by subscribing and clicking the bell button so you don't miss anything, as we upload new tutorials each week about Rhino and Grasshopper and how to use them specifically for architecture. As I mentioned in the beginning of the video, we'll use project Lane 189 by UNStudio as an inspiration for this tutorial, where we're gonna reproduce similar pattern but on a flat surface with rectangular openings. But for all of you who would like to go a step further, we prepared an extended version of this tutorial where you will learn even more advanced technique on how to create this kind of facade pattern but on a rounded surface, which is way more common but way more difficult to create. This you can watch it on our Patreon page and support our work at the same time. Alright. The first step will be to create modules that will be positioned on the facade based on the openings. If we take a look on the reference image, this is the elevation. This picture explains types of components this project has on the facade. I found only 3 of them, but in our case we will create 6 of them. So I draw them here. This is the first one. I think this is the second one, and I think this is the third one. Let me check. Yeah. So basically I added these 4 guys. So in total we have 7 models. I draw them in Rhino, and once we have them in Rhino, we are going to import them in Grasshopper. I will use component geometry. Right click and go set multiple geometries. I select the first one that you want to import in Grasshopper. So I already applied them in each container. And if I turn this on, here we have this completely solid component. This one represents the model which is less solid, up to this guy, up to this one. Alright, so once we have each model imported in Grasshopper, we're going to group them, and once we group, I'm going to mirror them. I'm going to mirror because I want to have even more variation of the models on the facade for the later on distribution. So I want to have model like this, and let's say like this. Okay, in order to mirror them, first I will group, then using bounding box, find the center of the bounding box. Bounding box actually it's a surface because this guy it's flat already. Then I'm going to use YZ plane, and that plane will be mirror plane, and the geometry I want to mirror should be this one. Alright, and here we have mirrored geometry, and here we have original one. These 2 guys I'm going to place in the merge component, and here we have, you can see these 2 groups with 13 objects. The same logic I will apply for each model. Okay, so once we're done with that, I'm going to flatten this and place all of them within one data tree. This one will be in the branch 0, this one in the branch 1, this in the branch 2, and so on. For that I'm going to use component endFine, and I will check flatten inputs. If we take a look, you can see we have 7 branches, and each branch contains 2 items. So each branch represents a different model, and these 2 items actually the original one and the mirror component. Okay, I'm going to delete this And here we have all of them in one data tree. All right, this is the first step. Another step is to create a flat surface with openings. I create something like this. You can apply as many openings as you want, and you need to import this in Grasshopper. Right click, set one surface, and you need to select just a single surface here. Okay, now I'm going to unroll it. Actually, it's already flattened. You don't need to use this component, but for advanced tutorial, for rounded surface, we need to use unroller. That's why I choose to use this one for both versions. Once we unroll it, we have this surface on XY plane. Now we need to generate hexagonal grid, and this is very important to understand the logic how we are going to generate it based on this surface. First, we want to generate hexagonal grid that it looks something like this, and the size of the hexagon of the grid should fit within our surface. And we need to find the logic how we are going to do this. Basically, the last one should be somewhere here. Let's say we want to create something like this. We already know dimension of the surface, but we don't know dimension of the grid that we're going to place. So this is dimension V of the surface, and this is U. I'm going to go here just to see these inputs. This is really important to see in one frame. All right, something like this. All right, so as I mentioned, this is V and this is U, this direction of the surface. Now we need to generate the dimension of the hexagon of this guy. This is the size of the hexagon. We can generate it based on V dimension. This is all about mathematics. Well, let's first sketch one hexagon here. So we have 6 of these dimensions. Let's call this guy H. So this line is H. In our case, V contains V, it's equal 5 times H, but H is actually, if we sketch a hexagon here, this is triangle, and we have another triangle here and here, something like this. So actually H is equal 2 times the height of the triangle of this one. This is the height of the triangle, and we know that height of the triangle is equal to A times square root of 3 divided by 2. And actually A, this is A. Sorry, maybe I should use another color. This is A, this dimension, and this is the A. A should be placed here. So we need to get that A based on this dimension. If you continue this, so 5 times H is 2 times height of the triangle, and this is 5 times 2 times A square root of 3 divided by 2. And the result should be, I said you don't need to set 5, just to be clear. I randomly choose 5. You can set 10, you can set 100, doesn't matter. Maybe instead of 5 we can use this n. N should be number of the hexagon along this direction. I will call it EY because it is number of hexagon along y direction. And this guy is this one. All right, let me continue here. Instead of 5, I will type EY times a square root of 3. Now we can easily get this number, because this one we set arbitrarily. We already have v dimension of the surface, and a is equal v divided by EY times square root of 3. Okay, and you can see it here. I arbitrarily set 15. It means we'll have 15 divisions along y direction. So I divided first by 15. This is EY, and we get a result. Now this result will be divided by square root of 3, as you can see it here. Okay, and this is A. I will change the color. This one is A, and A goes in S, which represents the size of the hexagon. For the EY, instead of plugging 15 directly in this input, I will add one more. Sorry, I accidentally closed the sketch, but I want to explain why we need to add +1 for the input EY. So this is EY. If we have a grid like this, the next row will finish here. So this part will be empty. In order to fill this gap, we'll add +1. Then it means we will have additional 1 here and additional 1. In order to fill all gaps, that's why we add +1. All right, so we have S, we have EY, now we need to generate EX. It means how many of hexagons we want to have in this direction. This is U direction, this is a V direction. I will keep sketching this grid. The distance between this point and this point in U direction represents A plus half of the A. I will explain why. This is our division lines, and this line shows how many divisions we are going to have. The distance between these two lines represents this A plus half of the A, or 3/2 of the A. If we sketch a rectangle, we know that this size is equal to the size of the hexagon. So this one is A, and you can see here this one is half of the A. So this one is A, this part is half of the A, and it's 3/2 of the A. You're going to divide U by 3/2 of the A, and you will get the following result. You can see here we take U and then divide. But if you remember, this is the A. Then we are going to use addition to sum A with half of the A, and the result here should be 3/2 of the A. And now this one will be divided with the U. Result, we are going to round. Here we get how many of these divisions we will have. In our case, I just want to be sure that we will not have any gaps. That's why I add +2, just in case to have enough hexagons in the grid. And now we have all three inputs. P will keep as default, and we get something like this. I will disable this just for a moment. Based on this input, we can control the whole grid. And every time the grid will almost fit within our reference surface. It's very important not to have gaps. That's why we add here +2. Let me show you if we didn't add +2, what will happen. You can see that here we'll have a gap. Or if we didn't have +1, then we'll have gap here, these gaps. So that's why we add +1 and here +2. Once we have hexagonal grid and the reference surface on XY plane, our next step is to sort hexagons based on the distance from their center point to their closer openings. So basically the curves closest to the openings will be in branch 0, then hexagons a little bit less closer will be in the branch 1, and so on. I will demonstrate here what we want to get. Something like this. So the red ones are the closest ones, then the dark orange are less closer, lighter orange even less, up to dark blue. These hexagons are in the branch 7 and they're furthest from the openings. So now we need to sort them in a separate branch. And this is the most difficult part, and I recommend you to watch it carefully. First, we'll check how many branches we have, or how many branches we want to divide these curves. Because right now they're in one branch, 533 items. And if we connect this guy with the tree statistics, in the C output we can see how many branches we have. So we want to divide these guys in 7 different branches. If we have even more, if we have one more module, and which we place here, just need to zoom in and go to plus or minus if you want to delete one of the modules, you will get a different result here. Then we want to equally distribute 7 divisions or 8 numbers within domain 0 to 1. And we have these numbers here. We can use a graph mapper in order to edit position of the hexagons later. I will explain why we need a graph mapper. You can use either graph mapper or you can just skip it and directly plug a range with the V input. And why actually we are creating these numbers? Our main goal in this step is to separate this set of hexagons into 7 different branches or 7 different group of curves based on their distance to the closest opening. And then based on that number, which is the distance, we can separate them into 7 different branches. For that purpose, first we'll create 7 different domains, and later on we can see in which domain that distance belongs. I forgot to mention this part. So basically we have surface, then we find edge of the surface, use naked edge, join them. So we have 3 edges or 3 curves. Then we are going to sort them, and the one with the biggest length we will remove from the list, and we keep just these 2 guys. Then the points, these guys. Actually, this is the center of the hexagon. We'll pull to the closest curve, one of these 2, and we'll calculate the distance. Here we have the distances from the center of each hexagon to their closest openings, and we can see the list here. Alright, based on this list we can create domain. So the closest distance is 0.416 and the large distance is 42,692. Alright, so based on this domain we're going to remap these numbers which we get from the graph mapper. Based on this list you can see that I didn't use here -1. That's why, because we're going to use component consecutive domains. And based on these numbers, we're going to create 7 different domains. this component actually create the number between this one. So this will be the first domain. Then next domain will be made from these two guys, and so on. That's how we get these 7 different domains. Now we are going to check in which of these 7 domains these distances belong. Alright, we can see these distances which we calculate, and if we use component phi domain, in the D we'll place these guys, in the N we should place these distances, and in the S we should set to false. I forgot to mention that here also it's important to set false. Okay, in the I output we'll get values from 0 to 6. It means that this distance belongs to this domain, the last one. Then this one belongs still to this domain, and so on. You can see here that we have an output from 6 to 0. This is really important, this output, because based on this guy we are going to create branches. Actually, each of these index represent corresponding hexagon. So index 0 will be later on placed in the branch 6. Index 1 again will be placed in the branch 6, and so on. For example, hexagon with index 158 will be placed in the branch 1, index 159 will be placed in the branch 0, and so on. Okay, how we can do this? We'll use component replace paths. So we want to change the data tree for the points from the center of the hexagons. That's why we'll place it here. And here we can get branches. Either you can connect this guy here, or you can use tree statistics and you will still get branches or the paths for each item. So here we place the data which we want to change the path. Here in S we should place a corresponding branch to each item, and in the R we will set in which branch each of these items will be placed. So the index from the branch 0 will be placed in the branch 6. This guy from the branch 01 will be placed in the branch 6. And this is the output. We have 7 branches. Branch 0 has 69 items, branch 1 has 62 items, and so on. And you may wonder why we sorted this, because now we are going to orient red ones. We are going to move solid panels. On the dark orange we'll place these guys, on the yellow orange this one, and so on, because we have the data tree where these guys are positioned. This is branch 0, 1, 2, 3, 4, 5, and 6. And now we have sorted points based on the openings. Once we have sorted points, we can create plane, and we are going to orient and position these guys on this grid of points. Once again, we'll use this one. If we check 7 branches, 2 items, and we're going to place first in the longest list, because here we have 69, 62, 58, and so on items, but here we have just 2 items. So we need to match this data tree, and in order to get as many items as we have here, I will use longest list. And don't forget to check wrap. Okay, and we also need to create XY plane for each of these modules. we can simply connect bounding box, and the center of the bounding box will be the origin of the XY plane. Okay, so now we have all three inputs which you need for the orient. Geometry will be these models, but if I connect with A, you can see that now we have the same items, the same number of items as we have points. It will be really easy to orient them. I place one step in between. It will help us to have a little bit more random position within each branch. So for example, this one, it's in the branch with the yellow points, and they will be randomly positioned within that branch. That's why I use a jitter with the same seed value for both of these lists and with the same shuffle strength. I pick number 1 to be completely shuffled. Okay, and if we connect these guys, this should be the models, this should be their center points, and C represent grid points. If I turn this on, we have this model position on the grid, but you can see these models are bigger than our hexagonal grid we have. So we need to find a way how to fit them in our grid. And for that, we'll use box morph. So in the G is the geometry which we want to fit or to morph. I'm going to flatten this and place in the G. In the R should be the reference box. And the reference box we can easily get by bounding box of each of these guys and extrude along set. Arbitrarily I set factor 1. And we have reference box. And the last thing which we need should be target box. Basically I just use the curves, these hexagons, with the bounding box, extrude with the factor 1, we get these boxes. And which is really important, don't forget this step, use the same logic for the replace path as we use for the points. Because now we'll get 7 branches instead of how many we have here, 533 branches. So it's really important to do the same thing. Alright, we have a bounding box for each hexagon, and we can directly connect with the T input, which is a target box, and we'll get appropriate result. But I want to make it even more complex. So I want to keep position of the red and the orange hexagons or the models, but I want to a little bit shuffle the rest of them. And we can achieve that by using explode tree. So this 0 and 1 branch we are not going to change, and we'll keep them as it is, having directly placed with entwine 0 and 1. But the rest of the branches, I'm going to place within one list and I'm going to flatten them. These ones. Now I'm going to sort them based on the distance from their center to these two curves. I will create component volume, then I will take out their center, and then the center I will pull to the closest curve. This guy, it's connected with the openings with these two curves, and here we have the distances. So these guys I'm going to sort by the distance, and I'm going to shuffle them, but I don't want to shuffle with high number, just maybe maximum 0.2. Here we can set the iteration. Alright, once we shuffle them, I will place in the branch 2. Now we will flatten the whole data tree here, because here we have as well flatten, and also here just one branch. I will place it here and you can check what we get. I will turn this off. This is more or less the result which we want to get. Models that are closest to these two curves are solid, and the ones that are furthest from these two curves represent this model. Sorry, this to represent this model. Now, once we have these models on the XY plane, we want to put them on the facade here, on our original surface. And again, we'll use orient. In the geometry for the orient, we will first group these guys and place in the G. We'll use XY plane. And you can see this XY plane, it's in the down left corner. That's why we're going to take out this corner on our original surface. I will create bounding box. Bounding box is connected with the reference surface. All right, then I will use evaluate, reparameterize, and set this point here. And this frame should be target plane. If I turn this on, we basically moved from the XY plane to our original surface, which we created in Rhino. I will turn this off. Now the next step is to cut this part and to cut this part. So we want to remove these two and these ones. So we don't want to have this one. Okay, if we check what we have inside this output, it says group with 533 objects. Because we cannot split the group, we need to ungroup it once and once again. Now we have surfaces and curves. All right, this is the original surface. I'm going to extract naked edges and join them because we need them to cut the surfaces and curves. And now I'm going to show you a method how we can separate curves and surfaces. We'll use component evaluate, and in the F we'll type this function. In the X we need to connect panel with the X. If you connect directly here, it won't work. So first panel and then panel in the X. Then we'll have a Boolean output true and false, and in the A we'll have the surfaces, and in the B we'll have curves. Maybe first we can cut the surfaces. So now I will turn off this. So here we have surfaces, and we're going to use component surface split. Don't forget to check graft, and the splitting curves are these guys, the naked edges of the surface. And you can see that we already cut the surface, but we need to take out unnecessary ones. As I mentioned, we need to remove this part, so inside these rectangles and outside the big one. Also, one cool trick how we can take out them. First, we'll place curves. Basically, we're going to convert surface to the curve. Then we'll take out its corners of each surface or of each curve. Once we have corners of each surface, we'll pull to our reference surface, or the surface we created in Rhino, this one. All right, here. So these points we're going to pull. We'll have as many distances as we have corners. So for this one, we have 4 distance because we're going to pull to the reference surface. And our logic will be if a mass addition of the distance is smaller than 0,1, then keep these items in the list. It means this guy, if we pull its corners to the reference surface, because they're already on the reference surface, distance will be 0, 0, 0, 0, and the mass addition will be 0. And we'll keep that surface in our list. But for this one, this one it's already on the surface 0, 0, but these 2 points are not on the reference surface and their distance will not be 0. So it's not 0 and this is not 0. It means we'll take out this surface. The output will be true and false values, but really important thing is to keep data tree same. You can check that we have here 2,972 branches, and these guys on this surface we have 2,741, so they're not the same. And that's why we need to shift paths. So we need to remove this path, the last one. And if we use shift paths with offset -1, we will get the same branches as we have here. And if we use call pattern, we will remove the ones we don't need. And you might say, okay, we already split, but there is one problem. In the corners, in this one, we have this small triangle. It means that our logic is not 100% correct, because this triangle has the corners that are already on the reference surface, but we don't want to have it. That's why we are going to import one more if function. So I will delete this. I will say if all corners of the surface are placed on the naked edges of the reference surface, remove it. In our case, this triangle has corners that all of them are placed on these naked edges of the reference surface. So that's why we're going to, in order to get a distance, we will take these points and pull to the naked edges, these 3 guys. And we have here distances, mass addition, in order to calculate the mass addition of the distances from each corner to the naked edge. And if the total is 0, then remove it from the list. And now we need to invert true and false values. So the true will become false and false will become true. Now we can use gate and combine these 2 Boolean values. I will delete this, we don't need it anymore. And with the gate and, I will sketch why we use gate and. Let's say we have here we have 0, 1, 0, 0, 1, 1, 1, 1. And this represent all the surfaces that I previously shown you, but some of these 1 has to be a 0. For example, this one. Then these guys are true, all of them except these 2 small corners. So for example, they're true, 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 false, true, true, true. How this gate and works, it combines 2 outputs and check if 0 and 1 it's always 0, 1 and 0 it's always 0, 0 and 0 it's 0, 1 and 1 it's 1. So only in this case the output will be true. And that's how we are going to remove the items that we have in the corners. 2 of these guys that were true will become false, because here we have 2 false items. And as I did previously, we need to shift paths in order to have the same branch numbers. I will take a look here. You can see that these branches are not the same. If we use shift paths with the -1, they have the same. And if we use call pattern now, you can see that these small triangles are removed. Once we cut surfaces, we'll cut the curves. Very similar logic. There are the curves. We'll use component trim with region. Basically, I take the bounding box of the original surface and just take out the naked edge, and this naked edge I place in the R. Here we have curves that are inside, and here we have curves that are outside. We'll use just the curves that are inside, but now we need to remove these two set of curves. Turn off this, and basically it's quite easy. The same logic as we did here. We'll take out the corners of each curve and pull on the reference surface and check if the mass addition of the distances is smaller than 0.1. We'll keep them, otherwise remove from the list. As the distance from the corners of these guys are bigger than 0, then this set of curves will be removed. And in the final output we have here curves, and here we have surfaces. For all of you who would like to go a step further, we prepared an extended version of this tutorial where you will learn even more advanced technique on how to create this kind of facade pattern but on a rounded surface, which is way more common but way more difficult to create. This you can watch it on our Patreon page and support our work at the same time. With that, you will also get access to all our extended tutorials and project files. If you are interested in a structured step-by-step learning approach with the personal one-on-one support 24/7 and homework exercises, feel free to send application for our Rhino for Architects online course and schedule your call with us where you will get more information about that. The first link in the description. The course covers various topics like parametric modeling with Grasshopper, fluid form modeling with SubD, architectural visualization, animation, presentation technique, and way more things. As we currently have a couple of available spots, I invite you to apply even today. I would like to send special thanks to all our Patreon supporters. If you like what we do, please consider becoming Patreon yourself, or you can simply hit the like button, consider subscribe if you haven't already, and hit the bell so you don't miss any future tutorials. Take care and see you soon.